Good evening. We start today our course for mechanical designer, and we start with the first block review, mathematical review, and I have thought it's interesting to start with rate of change because we're going to use it in the future, and then why I have thought it's interesting to review again. And what about in the next video? It's talk about derivative and differentiation is very important in mechanics and in scientist calculus. Then we're going to see the derivative and differentiation and some exercise in optimization. I mean the manufacturing using mathematical what we have studied now, and we're going to study in the next video. Okay, so now we're going to start with the rate of change. Rate of change. Okay. So we have two kinds of rate of change. We have rate of change medium and we have instantaneous. Yes. Okay. We have rate of change medium, and we have rate of change instantaneous. Okay, I explain. We have rate of change medium. It's just kind of rate is using inside the interval. I mean, we have in some interval you have some values, and we use this rate to calculate the values inside the interval. It's not precision, because we can define, for example, the time exact. For example, I explain. For example, we have here between A and B, we have take some values, any values, and calculate the interval. This is the inside interval. It's the medium. Rate of change medium. I mean, yeah. So we take in consideration all the values. It's not precision, But if you want, for example, now what happened here or anywhere there inside, exactly here in time. So here is the instantaneous. Yes. Yes. For example, I give you an industrial example. I give you, for example, you have a cylinder. A cylinder. Going back, Okay. So here, for example, he puts something here. It's industry. We have it's an industry, for example. We have a B and A. With the medium, we take all these values. Sorry, but with instantaneous, we should know all the time what happened here, and here. It's very interesting. Why? For example, maybe in some practical we are not interesting to the cylinder go all there and come back. Only for example here, only for that, only this distance. So we should know all the time what happened here. At what time he here, what time he here and there. Okay. It's for example we have a cylinder, pneumatic cylinder. Robotics use too much because we need speed, speed. It's why. But for example, when hydraulic, for example, we need the force. It's normally it's a liquid. It's when they go and push. We need the force. Too much force to push it here. If it's high, But for example, when you in robotic and something like that, we need speed. He go out and come back quickly. Then maybe we are not interested to come back at here. That's for example here. He come back here only. And here, this distance is this time. This time we need this time to go back. We talk about that in future. So, okay. So for this problematic, I have choose a couple, for example. To explain it easy, it's simple. Now we're going to see the rate of change medium. Okay, so for this, for example, we have increase of bacteria. This bacteria increase with this formula pt with this function 1 plus t square. So when t is a time increasing and p is a value of the increase in time at the time t. So for this, for example, we're going to do t equals 0, t equal 1, t equal 2, t equal 3, and t equal 4. So in our function we put here t equals 0, we have 1 bacteria. And t equal 1, we have 4 bacteria. 2, we have 9 bacteria. 3, we have 16 bacteria. And 4, we have 25. Okay, bacteria. So we do the table, T, P, T. We have 0, 1, 2, 3, and 4. Okay. And 0, you have 1 bacteria, and 1, 4, 9, 16, and 25. Okay. So we're going to calculate here rate of change medium. Rate of change medium. Okay. It's what? When you have, before we have talked about it, it's you work in interval, you know? Should be interval here. For example, this interval. This one. 0, 1. Rate of change is P4 minus P1, 4 minus 1. Interval 0, 1. So 4 minus 1, 1 minus 0. It's 3 bacteria. Okay. So here we have Here we have 3 bacteria. In time, 60 seconds, 1 minute, 60 seconds. Here same. For example, here we take this interval, 3 and 4. Okay, we have 60 seconds again. Okay, so it's P4 minus P3, 4 minus 3. It's P4 is 25 minus 16, 4 minus 3. So it's 9. So here we have 9 bacteria. Okay, okay, fantastic. So now for example, we have here 60 seconds. 60 seconds we have 9 bacteria, but what happened in 30 seconds? Who can tell you, for example, here we had 6 bacteria and here 3, or here 5 and here 4, no? In this time, I mean. Nobody can tell you that. Why? Because it's a rate of change medium. So we have it nothing exactly. We work in interval of time, but not in definite time. It means, for example, in 4 minutes, 3 minutes, 2 minutes, we don't know what happened. For that, we use the rate of change instantaneous. Okay, what is the rate of change instantaneous? It's a limit of our function pt minus, for example, we take t for 4 minutes minus p4 t minus 4. Okay, it's a limit at 4th minute t tend to 4. pt is our function 1 plus t square minus p4 is 25 minutes t minus 4. Okay, this is its identity 1 plus t square, it's t square plus 2t plus 1. Okay, it's a limit when t tend to 4, t square plus 2t plus 1 minus 25 t minus 4. Okay, it's limit when t tend to 4, t square plus 2t minus 24 t minus 4. Now we choose this one, t square plus 2t minus 24 0. Delt, it's 2 square minus 4 1 minus 24. It's 100. But x1 it's minus 2 minus 10 2 is minus 12 2 is minus 6. x2 it's minus 2 plus 10 2 is 8 to 4. So our equation now is a limit when t tend to 4, x minus 4, no x no, it's t minus 4, t plus 6, t minus 4. So here simplify here is our equation now, limit t tend to 4, t plus 6. Where plus here we have result, it's 10. This is its rate of increase of change instantaneous. Okay, it's simple. It's a simple calculation limit. It's not nothing complicated. It's limit. Okay. Now we're going to do another example. 2 examples is better than 1. Okay. Now we threw a stone in the lake and we have formed a circle around the stone like that. For example, a stone here, we have circles, you know. We have more circles, but we take in consideration only 4 circles, you know. Only this 4. Okay. We have 4 circles. We have rad 1, rad 2, rad 3, and rad 4. We do same. We have a rate of change medium. It's between the 4th and the 1st circle. It's we have our function. This is a circle of function fr. It's here p r square. It's because we have a circle. Okay, we have p4 square minus p1 square 4 minus 1. We have 16p minus p under 3. We have 15p under 3. We have 5p m square in m radius. Okay, this is a rate of change medium. Okay, now we do the same. We go to the rate of change instantaneous. It's it's a limit. For example, we take like example in the fourth. No, we're going to do the general formula. Then you use it everywhere. For example, if you have the radio is changed to air to A. Now, this is a variation, you know. So it's a limit R to A, P R square minus P A square R minus A. It is our equation. So it's limit R to A is P R square minus A square under R minus A. Its limit R to A. This is identity R square minus A square. It's R minus A, R plus A. Okay. Its limit P R minus A factorial the R plus A. Okay. It's under R minus A. Okay. Now we simplificate. We have our equation. It's limit R to A. It's R plus A. And P. Don't forget it. You replace A. We have 2PA. This is rate of change instantaneous. Okay, this is rate of instantaneous. So for example, we have four circuits, so A equal 1, A equal 2, A equal 3, and A equal 4. Okay, when R equal 1, we have 2P. R equal 2, it's 4P. R equal 3, 6P. And 8P. Now we observe the result is linear. Why? Because we are talking about circle, you know. It's symmetrical. This part and this part, they are the same. You should always observe your result. It's not, we don't focus only the numerical. It's what happened now. You have, when you should observe your result all the time. Okay. Well, now we're going to start with the instantaneous velocity. Well, here is practical too. So we have, for example, we have a distance, this distance A to B, A to B. Okay, x0, x1. Okay, a car start here and finish here. You know, so you have this. It's distance, and here, for example, time. Sometimes it's like that, sometimes it's like that. So, well. And the same things, we have the velocity medium and velocity instantaneous. The medium is like same. Is we take, for example, this. We take this interval. You know, this interval. It's a medium. So we take consideration all the values here. Now, when he was 50 kilometers per hour, 100, and do you think we know especially what happened here? No, it's impossible because you have to take all the values. So it's like before, velocity medium. It's distance per time. It's okay, because here we have, in the beginning you have x0 is xt, and the x1 is there, it's t plus del t. Okay, so if you want to know exactly what happened here, or here, or here, or here, you should use the instantaneous velocity. For example, we have, like before we have telco, you have a gear, for example, now we're here. More because we have 0.5 in the airport. Yes, here we have, for example, a point E. For example, we have here another point here, here. So we should know all this point when they arrive here. See why? Because we should control the movement. If you don't control the movement, you don't control our design. You know, it's a system. It's very important. If you have designed it, you should know what is how the system work all the time. You know, if you haven't designed it, you should understand it. So it's very important to understand the system, how he work. Okay, in this case we are talking about speed. Here it's not linear speed; it's omega. It's the t. Is 2pf, where f is 1t. Okay, it's another, it's angular. Okay, but it's speed. Okay, it's y. It's like what I have told before. We have a cylinder going back, pushing I don't know what, or I don't know. We should know all the time what happened here, all the time here and here and here, and you do your curve. Then you study properly your system. Okay. Okay. So we talk about the velocity, the instantaneous velocity. Its limit when del t tend to 0, we show the distance, you know. It's t plus del t minus xt. So del t. Okay. Now, for example, for this example, I'm going to use this movement is uniformly accelerate. Then we use the function xt equal 5t squared. This is equation movement. Okay. So our question will be limit when del t tend to 0. It's 5t plus del t square minus xt is 5t square under del t. Okay. It's limit when del t tend to 0, 5, this is identity to t plus del t square, it's t square plus del t square plus 2t del t. Okay, it means 5 t square plus del t square plus 2t del t minus 5 t square and del t. Okay, it's a limit when del t tend to 0. Here we simplify. Okay, we have 5 del t square plus 2t del t. Okay, here this question will be limit del t to tend to 0. It's 5 del t del t plus t plus 2t, and del t here. We simplify here, so equal limit del t tend to 0, 5 del t plus 2t. Okay, so it tend to 0, so the result it's 10t. So here it's instantaneous velocity. We replace t values, and then we have the instantaneous velocity. It's nothing more, it's nothing special, it's like that. Okay. Here now we're going to see tangent equation. Okay, we have our axis. Our axis here. Our curve. And our diagonal, yes, angle. Have our point here, A, 2, 1, U, X. Okay. Okay. We have, for example, we have a point A equal to 1. For example, we take a point, for example, B, 3, 4, and our slope is M, it's U, B minus U, A, X, B minus X, A. It means 4 minus 1 and 3 minus 2 is 3. M 3, our slope. Okay, now our tangent equation. We have u minus 2 and x minus 1 equal our slope 3. U minus 2 equal 3 x minus 1. U equal 3x minus 3 plus 2. U equal 3x minus 1. This is our tangent equation. Okay. We have alpha is between D and OX, and what you should know, it's M equal tangent alpha equal UB minus UA XB minus XA. This is what you should know. It's what you know that, but it's a review. Okay. And today I think we have finished the review, and I hope to see you next week. It's the beginning of the review. After that, like I have told you, next week you have derivative, and differentiation is very important in mechanics and in numerical scientist calculus. Yes, and what is the we do again I say again, optimization. Then we see how we use mathematical, what you have studied in this course and the next course, to use it to manufacture. Okay, we define the geometry for our conception. You know, for example, you have boxes, so anywhere how you use mathematical to define the geometrical and the size of the boxes, for example. Okay, I hope to see you next week. I think it was benefit this one, and for the next.